welcome to 3.5, page 2. We're going to be talking about half-lives here, and perhaps you've had a chemistry class, maybe even a biology class, but where it talks about half-lives. One of the things that gets in people's way a little bit is we have this radioactive isotope 226Ra. That's just the name of it. That 226 is not a player in this problem whatsoever. The half-life, the initial quantity, the amount after 1,000 years, the 1,000, those are all players. But this is just a name. We don't even need to see this. We just need to know there's some isotope that has a half-life of 1,600 years, an initial quantity of 10, and the amount after 1,000 years is what we're looking for. So what this means is we start with 10 grams, and I don't know how we've measured this, but after 16,000 years approximately, this is like figuring out the age of dinosaur bones, which there's some theory in that, but after 1,600 years, this 10 grams will cut to 5 grams, and after another 1,600 years, it'll cut in half again to 2.5 grams, and after another 1,600 years, it's going to theoretically cut in half again. Well, we're only going to go 1,000 years. Let's make some sense out of this first. If we're going 1,000 years, we're not getting cut in half a full time, but we're going to reduce from 10. I would expect the answer to this to be more than 5. So let's see if we can make some sense out of this. The amount after time passes, the amount after 1,000 years, would equal our initial amount. I'm going to call that A0, amount at time 0. And what are we doing? We're multiplying by a half. And then we're multiplying by a half again. And if we go 7 half-lives, we're going to multiply by a half, times 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 a half. At some point, we're going to realize it sure makes sense to use an exponent here. But here's the challenge. I'm not even going to multiply by a half a full time. What amount of time am I going to, or what exponent do I need if it's just 1,000 years out of 1,600? It's that fraction. And what is this? The actual amount of time over what is this? The half-life. That's our formula right there. Definitely worth understanding that. And I'm going to try to go through that again as we go through 26, 28, and 30. But it's not a formula that a mathematician needs to memorize. To be honest, a lot of science people have taken this problem and this formula and converted it into something more like this, and we'll talk more about that a little bit later, where we use E, and then they just use that generic formula for all problems. But we'll talk about that in a little bit. So here we go. I want to know the amount after 1,000 years. I want to know A1000. I'm told that the initial quantity is just 3 grams. So I've got my initial. I'm looking for my amount after time passes. I'm going to start multiplying it by half. Now let's think about that for a moment. Here's where the making sense of it matters. I might multiply this by a half a bunch of times, but not in this problem. It takes 5,730 years for me to multiply it by half. I'm only going to allow 1,000 years to pass. It's a smaller fraction than 1. It's this fraction. The amount of time that passes divided by 5,730. I'm just multiplying by a fraction of a half. So let's get to that. 3 times 0.5 raised to the 1,000 divided by 5,730. So let's make sense of this before we hit the enter key. You might have already done that, but let's make sense of it. I start with 3, and it's going to start reducing. No doubt this is going to be less than 3. But I'm not multiplying by a full half, and half of this would be 1.5. I'm multiplying by a small fraction of a half. So it's going to be less than 3, but it's certainly not going to get down to 1.5. And I get approximately 2.658, which is reasonable. Less than 3, but didn't get multiplied by a full 1/2. And The reason I'm stressing that is because when people make errors on these exponential types of problems, usually the error makes no sense. Like I'd get an answer here of 0.00029, or I'd get an answer of 57,000 or 5,200 years, or 5,200 grams in this case. This is grams amount. You get answers that don't make sense. It's the same with investment problems. If you invest $100 at 3% interest for 12 years, you're not going to get $74 billion. But a lot of times on story problems, I get answers like that where you need to go back and rethink it. So we'll stress that a little bit here. So here, the half-life is given, 24,000 years. The initial quantity, the A0, amount at times 0, I don't know. But I do know that we end up with 0.4. What I'm looking for is the initial amount, which is going to be multiplied by 1/2. How many times? Just barely at all, really. Just a tiny fraction. It takes 24,100 years to multiply by a full half, and we're only allowing 1,000 years to pass. That is the fraction 1,000 on 24,100, which we could certainly reduce. I'm just going to carry it along and deal with it in my calculator. So I need to divide this away. So I get the amount at times 0 equals 0.4 divided by 1/2, or 0.5 to the 1,000 tiny fraction of the full half-life. And clearly we could have reduced 2 zeros there. So 0.4 divided by 0.5 raised to the, don't hit equals yet, let's talk about this, 1,000 divided by 24,100. Now this is what it reduced to. Some time passed, not much of the half-life, but some time passed and it reduced to 0.4. I expect this to be just a little bit bigger than 0.4 because only only 1/24, virtually 1/24 of a 1/2 was being used to multiply here. And sure enough, 0.412 grams could go there. Just a little bit more than 0.4, it made sense. All right, 30. This answer might take some convincing to you that it makes half when we go through problem number 30. Okay, just like 28, the half-life is given just 87.74, which is a human lifetime. However, in half-life terms, not a whole lot. And compared to 1,000 years, we're multiplying by, we're cutting it in half a bunch of times here, 12, 13 times, 12 times in half. So here we go. The amount we end up with is 0.1. I want to know the amount we start with. I want to know A0, or initial amount. We're multiplying by 1/2. How many times? A bunch. Every 87.4 years, it gets cut in half, and we're going 1,000 years. That means I want 1,000 divided by 87.74. So this becomes, it's a mess, but A0 equals, it was 0.1, and I need to divide by 0.5 to the 1,000 divided by 87.74. As I said, this might startle you with its size, but we'll come back and talk about that. 0.1 divided by 0.5 to the 1,000 divided by 87.74. And we get, okay, so you're telling me it's 269.732. That's A0, that would be grams. You say, wow, that's pretty big. Well, remember, I mean, we got all the way down to 0.1, but it was divided by 2 a lot. Watch this. Divided by 2, that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And when we say close to 11, 12, in the 12 times ballpark. And so there we are, we're getting right, we're approaching it right there. So actually is a reasonable answer. Okay, I'm going to take you back to this formula that we used for interest rates, where the amount we end up with equals the principal, what we start with, e to the interest rate times the amount of time we leave it in. And I'm going to just jot that here. If this was an investment here, what we'd start with is the amount at time 0, 1. So maybe this P is just like having $1. And then we end up with $10 after 3 years or something like that. But I'm going to show you how these are exactly the same formulas. So let's go. I'm going to substitute 0, 1, find the exponential model y equals ae to the bx, which means I need to figure out what a is, and I need to figure out what b is. I know what e is, it's just a number, and y and x are, that's our coordinate axis that we're dealing with. So I'm going to put 0, 1 into this formula for x and y. 1 for y equals ae to the b times 0. And the beauty of this is it eliminates the b, and I can figure out what a is. So 1 equals a, e to the 0th is 1 times 1, a is 1. Oh, well, take a look. A right here is the same as P right there, which is, hey, how much did we start with? A is going to be 1 here. Now I'm going to let you come back and finish this one, problem 31, because that's an odd problem, but I'm going to do the same thing here. Now we won't always start necessarily at 0, 1. This might be 0, 6, but if it's 0, 6, A is 6. A is 1 here for the same reason A was 1 there. So here we go. A equals 1, so right now our formula is y equals 1 for emphasis, e to the bx. And now I've got another point right here, and I need to know what b is. What could I possibly do with the 4, 5? Well, I can put 5 in for y and 4 in for x. So I get y equals e to the b times times 4, or e to the 4b equals 5. And I need to solve for b, but it's in an exponent, so I need a logarithm. Our base of that exponent is e, so I'm going to ln both sides, and that gives me 4b equals ln 5, or b is ln, careful, not 5/4, but ln of 5 all over 4. The best answer to this is this: y equals 1 e to the ln 5 on 4 times x, because that's what b is exactly. It will not surprise me if the back of the book has that rounded, or our solution guide, which is on the website or back of the book. So let's see, ln 5, close those parentheses, that's a common mistake, divide by 4. Will not surprise me if they have this as y equals e to the 0.4024x, something like that. However, our best answer is that. That will lead us to exact answers. If I put in 1,000 in here for x, I'm going to get the exact answer. If I put 1,000 in here, I'm now get a multiplied, exponentially growing rounding error. As we go on, it's going to continue to get bigger and bigger. Okay, same exact problem. Y equals, here's our formula, ae to the bx, but when x is 0, ae to the b times 0, y is 5. E to the 0th is 1, so a is 5, so our formula becomes y equals 5 e to the bx. But I've got another ordered pair. It's exactly the same as the graph. We're just given data, which, to be honest, in the real world is what you're going to be given. They're going to say the population in Rockton in 1980 was 2,470. The population in 2000 was 5,130. If we're assuming that's growing exponentially, they've just given us two ordered pairs. That's the way real world problems work in this sense, is more like this, where this could be year 0, year 3, population 1, population 2. So what do we know though? We know that A is 5, because at year 0, that's our starting amount. What can we do with 3 1/2? Put that in for X and Y. Put them in correctly. 0.5 for Y equals 5 e to the b times 3, or 3b. So e to the 3b equals 0.5 divided by 5, which I can't resist not reducing. E to the 3b equals 0.1 ln, and I get 3b equals ln 0.1, or b equals ln 0.1, not 0.1 on 3, ln 0.1, all on 3. So let's see what we've got here. Best answer, y equals 5 e to the ln 0.1 on 3 times x. Best answer. But to check book answer, I believe you'll need to do this. ln 5. Let's see what we got here. Yeah, we're good. Sorry, I was just looking back up at the previous answer. So we've got ln 0.1 divided by 3, and we get y equals 5 e to the negative 0.7675 x. That might be the answer. You say, oh, can we have a negative exponent like that? Well, let's think about it for a minute. If I looked at the graph of this, 0, 5 up here, 3 1/2, oh yeah, this is exponential growing down. It should have a negative exponent. Okay, that was a 17-minute video. I suspect it will take you maybe a little bit less time than that, and let me know what I can help with.